Welcome back to class, everyone. Let's just dive right into today's explainer, where we are finally making the big transition from abstract kinematics to applied dynamics. We've spent plenty of time describing exactly how objects move, calculating velocities, charting trajectories, all that good stuff. But today we finally look under the hood to answer the absolute fundamental question of classical mechanics. Why do objects move the way they do in the first place? Here is our syllabus for today. We'll be looking at the science of motion, Newton's three laws, frames of reference, mastering force diagrams, and then capping it off with real-world applications. Let's jump right in. Section 1, the science of motion. Before we start crunching numbers and calculating forces, we really need to ask how we actually investigate motion. Well, the answer lies in the scientific method. This iterative process is what evolved our understanding of motion all the way from Aristotle to Galileo. See, for nearly 2,000 years, Aristotle's view pretty much dominated. Everyone thought an object's natural state was just to be at rest, and that it required a continuous push to keep moving. But then Galileo comes along, uses some brilliant thought experiments, and observes that objects on frictionless surfaces wouldn't actually stop at all. It's exactly this systematic method of observation, hypothesis, and refinement that allows physics to identify universal laws applying to literally everything, from a simple falling apple to the orbit of entire planets. Now, to ensure our dimensional analysis is absolutely flawless before we start problem solving, we have to anchor our measurements in precise SI base units. In classical mechanics, our entire framework relies predominantly on just three fundamental units: the meter for length, the kilogram for mass, and the second for time. Keeping these standardized is crucial. It ensures that our subsequent calculations of force and acceleration are globally consistent, and trust me, it will save you a lot of headaches later. Section 2. Newton's three laws. Let's see how this all builds into the foundational rules published back in 1687 that literally govern our reality. Every body perseveres in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. That revolutionary statement is Newton's first law, and it completely challenged millennia of human intuition by proposing that a force is not required to sustain motion, but rather to change it. Essentially, if an object is moving at a constant speed in a straight line, it's going to do so forever unless an external force intervenes. It gives us a crucial conceptual definition. It defines the very job of a force. So, the real takeaway here is physical inertia. I always like to think of it as the stubbornness of mass. It strongly resists any change in its velocity. Think about a massive boulder. It has huge inertia, making it incredibly difficult to start rolling, but once it is rolling, well, it's equally stubborn and incredibly difficult to stop. Mass is simply the quantitative measure of that exact stubbornness. Skipping ahead to Newton's third law for just a second, we really have to drop a major misconception here. Action and reaction forces do not cancel each other out. Why? Because they act on entirely different bodies. For every action, there's an equal and opposite reaction. If object A pushes object B pushes back on object A with the exact same amount of force. Period. It is genuinely fascinating to spot these action-reaction pairs in daily life. Think about a rocket launch. The rocket engine pushes the exhaust gas violently downward. That's our action. The equal and opposite reaction is the gas pushing the rocket upward. Total momentum is perfectly conserved. It's the exact same physics that explains why a heavy 5-kilogram rifle kicks backward at 1.6 meters per second when it fires a tiny 10-gram bullet forward. Section 3. Frames of reference. So, what happens to these precise, beautiful laws when the observer's environment is accelerating? You know that feeling when you're in a car that suddenly hits the gas and you feel pushed back into your seat? You're actually experiencing what we call a fictitious force. That's because the law of inertia appears to be violated when you're in a non-inertial, meaning accelerating, frame. In a smooth, constant velocity inertial frame, Newton's first law holds perfectly. But in that accelerating car, your body's inertia just wants to stay at rest, while the car literally moves forward around you. You feel pushed back, but there's actually no physical force pushing on your chest. Section 4. Mastering force diagrams. Okay. Let's get methodical and adopt a framework to translate all these concepts into actual mathematical solutions. Just like we do on the chalkboard in class, you have got to rigorously follow these systematic steps to deconstruct any dynamics problem without getting totally lost. Step 1, identify all the interacting forces. Step 2, set up a smart coordinate system. Step 3, draw a free body diagram to isolate the object. And step 4, apply Newton's second law. That is, set the sum of your forces equal to mass times acceleration. F equals ma. By isolating an object in a simple free body diagram, it becomes completely intuitive. Take a stationary hanging mass. We draw it as a simple dot. The upward tension from the string pulls up, and gravity, the weight, pulls down. Because the mass is stationary, we know its acceleration is exactly 0. Therefore, those upward and downward forces must be perfectly balanced to achieve equilibrium. It really is that straightforward.
Section 5, Real-World Applications. As we dive into Chapter 5 of our text, let's start applying Newton's second law directly to the things we interact with every single day. Now, while gravity is a fundamental force, most of our daily interactions actually rely on what we call derived forces. I'm talking about friction, tension, or the normal force. These explain the mechanics of cars, elevators, you name it. But here's a wild thought. When you rest a heavy textbook on a table, the normal force stops it from falling through. But at a fundamental level, that macroscopic normal force is actually the microscopic electrostatic repulsion between the atoms of the book and the atoms of the table. Pretty amazing, right?
Let's test your physical intuition with one of the classic scenarios from Chapter 5. Imagine a half-kilogram pendulum hanging from the ceiling of an elevator. When the elevator is moving at a steady velocity, the tension in the string is just balancing the pendulum's weight, around 4.9 newtons. But what happens to that exact tension when the elevator suddenly accelerates upward at 3 meters per second squared? Think about that for a second. Well, if we stick to our step-by-step method, we can prove the tension absolutely must increase. Why? Because the string now has to support the static weight and provide the dynamic upward acceleration. Applying F equals ma, the sum of the forces in the y direction equals upward tension minus downward weight, all equaling mass times our new upward acceleration. Run those numbers and the tension spikes to 6.4 newtons. The string is literally working harder to accelerate the mass upward.
Okay, but what if the elevator accelerates sideways? This is where Newtonian mechanics shows its sheer robustness. If you solve this from inside the accelerating elevator, you're a non-inertial observer. You have to invent a fictitious force pushing the pendulum to the side to explain its angle. But if you're standing on the ground outside, an inertial observer, you just use standard F equals ma, knowing the horizontal tension is what's causing the acceleration. The brilliant part? Both methods calculate the exact same pendulum angle, 22.2 degrees. No matter your frame, the math works.
All of this actually leads us to a pretty profound philosophical question to ponder before our next lecture. If Newton's second law, F equals ma, allows us to perfectly calculate an object's future trajectory based purely on its present state and the forces acting on it, does that mean the future of every object is already predetermined? Do we live in a strictly deterministic clockwork universe? Think deeply about the implications of that as you review today's notes. Thanks for joining me for this explainer class, and keep questioning the mechanics of the world around you.